Welcome. So today we're embarking on a real blueprint and myth-buster journey into the foundational rules of radicals. This is specifically geared for grade 8 and Algebra A math. Now, if you've ever stared at a square root symbol and thought, okay, how exactly does this thing behave when I start adding, multiplying, or, trying to simplify it? Well, you are absolutely in the right place. In this explainer, we're going to build your mathematical blueprint right from the ground up, and then we are going to bust some of the most common myths and traps that literally catch everyone off guard.
Okay, let's dive into this. Here's our roadmap for today. First, the inverse of squaring. Second, factoring out perfect squares. Third, operating with radical expressions. Fourth, avoiding those common radical mistakes. Fifth, verifying solutions by squaring. And finally, number 6, a quick recap and transfer.
All right, section 1, the inverse of squaring. Before we can start manipulating radicals, we really need to understand exactly what a square root is actually doing. It's not just some random math symbol, right? It's a very specific mathematical action.
To really get radicals, we just need to run some basic arithmetic in reverse. Think about it. When we take 5 and square it, which is just multiplying 5 by itself, we get 25. The square root symbol is basically playing Jeopardy with that math. It's looking at the answer and asking, hey, what non-negative number, when multiplied by itself, gets me back to 25? And the answer, of course, is 5. So the square root of 25 is 5. It's just the direct inverse operation of squaring. They perfectly undo each other.
But listen, we really have to set up a firm mathematical guardrail right here at the start. We are operating strictly within the real number domain. What does that mean for us? It means the values inside our square root, the stuff we call the radicand, must be non-negative if we want a real number as our output. Why is that? Well, because any real number you square, whether it's positive or negative, is going to result in a positive number. You literally can't multiply a real number by itself and get a negative result. So trying to find the real square root of a negative number, yeah, that just won't work in this domain.
Let's move to section 2, factoring out perfect squares. So now that we know what a square root is, how do we handle numbers inside the root that aren't nice, neat, perfect squares? Well, this is exactly where we learn to simplify.
We simplify radicals using a highly reliable 3-step sequence. Imagine you're looking at the square root of 12. 12 is definitely not a perfect square, but step 1 tells us to find the largest perfect square factor of 12. That would be 4, right? Step 2, we simply rewrite the expression inside the radical as a product. So it becomes the square root of 4 times 3. Then, step 3, we extract the root of that perfect square. The square root of 4 becomes a nice, clean 2 on the outside, leaving that 3 safely tucked inside. So the square root of 12 simplifies to 2 times the square root of 3. We intentionally keep this cognitive load super light. It is always just find, rewrite, and extract. Easy.
All right, section 3, operating with radical expressions. We've simplified our tools. Now let's actually put them to work in our algebraic toolkit.
So here are your valid operational rules. First off, for addition and subtraction, you can only combine the coefficients if you have what we call like radicals. That just means the number inside the root is exactly the same. It's kind of like combining matching triangles or matching squares in a video game. Now, for multiplication, the rule is totally different. You multiply the outside terms together and the inside terms together. And here's the cool part. These exact rules apply whether you're dealing with whole numbers or rational number coefficients, like fractions and decimals. The rules stay exactly the same.
And this example brilliantly illustrates that addition rule we just talked about. Let's take 2 times the square root of 3 and add 4 times the square root of 3. Because the radical itself, the square root of 3, is absolutely identical in both terms, we simply add the numbers out front. 2 plus 4 gets us 6 times the square root of 3. I like to think of the square root of 3 as a physical wooden block. If I have 2 of those blocks, and you walk up and hand me 4 more blocks, I now have 6 blocks total. The radical itself doesn't change at all, just a quantity of them.
Moving on to section 4, avoiding common radical mistakes. Welcome to the highly anticipated Mythbuster arc of our explainer. Mathematics is full of these intuitive leaps that, honestly, turn out to be completely false. We're going to preemptively correct the most common, deeply tempting assumptions that students make with radicals.
Okay, here is the absolute biggest trap in Algebra 1. A direct question for you. Can we just split addition inside a square root? Like, if you see the square root of a plus b, does that equal the square root of a plus the square root of b? Your brain really wants that to be true, doesn't it? Because it just looks so neat and tidy.
Well, let's bust this myth wide open with some real numbers. If we have the square root of 9 plus 16 all under one roof, we add those together to get the square root of 25, and the square root of 25 is exactly 5. Simple enough. But what if we try splitting them up? The square root of 9 plus the square root of 16. That evaluates to 3 plus 4, which is 7. And guys, last time I checked, 5 does not equal 7. There's just no way. Therefore, the square root of a plus b is generally never equal to the square root of a plus the square root of b. You just cannot split addition across a radical. It's a huge no-no.
And here's our second mythbuster for the day. What happens when we have unlike radicals? Say 2 times the square root of 3 plus 4 times the square root of 5. Can we just smash those together and make it 6 times the square root of 8? Absolutely not. Think back to standard algebra. If you have 2x plus 4y, you can't just combine them into 6xy, right? Because x and y are entirely different variables. Well, radical symbols act the exact same way. The square root of 3 and the square root of 5 are completely different values. Because they are unlike, they simply cannot be combined.
That brings us to Section 5, verifying solutions by squaring. So, how do we know we haven't completely broken math along the way? In algebra, the absolute best way to confidently move forward is to ensure you know how to safely check your work in reverse. We do this by squaring our answers to see if we get right back to where we started. Let's do 2 quick checks here. Check 1. Earlier, we simplified the square root of 12 to 2 times the square root of 3. If we take that whole expression and square it, well, 2 squared is 4, and the square root of 3 squared is just 3. Multiply 4 times 3, and that gets us perfectly back to 12. Boom, it works. Now for check 2. Let's take 5 times the square root of 2. Square the 5 to get 25, and square the square root of 2 to get 2. 25 times 2 is 50, which tells us our original radical was the square root of 50. By squaring our outside and inside terms, we can confidently verify our math every single time. And finally, Section 6, recap and transfer. So the crucial point I want to make here is that mastering these operations, it isn't just about memorizing random symbols. It's really about understanding the underlying structure of inverse operations and applying a few strict logical rules. Let's rapidly fire off the golden rules we cemented today. Rule 1, always connect square roots to their inverse, which is squaring. Rule 2, simplify by hunting down and extracting those perfect square factors. Rule 3, when you're adding, only ever combine the coefficients of perfectly identical like terms. And Rule 4, our absolute golden mythbuster, never ever try to split addition or subtraction inside a single square root.
As we wrap up this explainer, I really want to leave you with a final thought to chew on. These rules we went over today, they aren't just for simplifying random numbers on a worksheet. Think about the Pythagorean theorem in geometry, or the quadratic formula when you start factoring higher-level polynomials. How will your absolute mastery of these specific radical rules unlock your ability to solve those incredibly complex properties down the road? Think about it. If you truly understand what we covered today, you're already holding the keys to the rest of algebra. Keep exploring, keep questioning, and I'll see you in the next explainer.